believe in the last lesson said I did arc sine of x, the derivative of arc sine of x. So let's do arc tan now and kind of rehash that process and the questions that went with it. Then after that, some real basic, straightforward questions, half of a lesson set that I gave to students to go to the board, and then we'll do the other half. I guess the next lesson set after this one. All right, so I asked what these variables stood for in the last lesson set, and I hope you know. In this language, that's a ratio. And all we do is go from angles to ratio, or from ratios to angle. I mean, that's basically what the major operations are in trig. Right? And so that's a ratio. It doesn't look like one. Do you remember what I did to make it look like one? Yeah, I put a 1 under. So if that's the ratio, then we're finding angles that produce those ratios in the tangent function, which means that we can isolate x by saying that x equals the tangent of y. Now, that's an angle. It's still an angle. So we have a nice picture here, I hope. There's my angle y. There's my x to 1 opposite to adjacent ratio. And with the Pythagorean work we did in Algebra 1 lesson sets, and also in the last one, 1 squared plus x squared is this square area. Therefore, that length is the square root of that area. And that allows us now to answer the question, if we do implicit differentiation, the intermediate step is 1 times dx equals secant squared y dy. And that's multiplication, which becomes division on this side. It's a y, ugly looking y. And multiplication by dx on this side becomes division on that side. And so now we have our derivative. If we can figure out what the secant of y is and then square it and put it in the denominator. Well, secant is reciprocal of cosine, and here's our cosine, 1 over the square root of 1 plus x squared. I guess 1 over the square root of 1 plus x squared, and if we square that, I think we're going to get rid of the square root symbol. So dy dx is equal to 1 over 1 plus x squared. And I think if we did, well, let's do something up here now, and then we'll give you a problem to try here with the chain rule. And hopefully that will be another flashcard moment for today. And if we include it in our future lesson sets and make you work with it on a daily basis, you will hopefully put it in your longer term memory. All right, arc sine of 2x. What's the derivative of arc sine of 2x? Derivative of what's inside over the square root of 1 minus what's inside gets squared. I don't think I have to write all this out. I'll just talk you through it, and that's practice for that today. How will we get approximation for the cube root of 64.1? Well, cube root is the inverse of that graph. And the inverse of that graph, if we, I wish I had a piece of paper. I'll do it in the next lesson set where you switch the x's and the y's. You get a graph that looks like this. And so we're over here, and we're trying to find 64.1. Well, I know what 64 gets me. It gets me 4. The cube root of 64 is 4. And if I draw a tangent line, it's almost right on top of it. Well, it is on top of it, but it almost mimics it completely, at least in the near run here. I mean, it eventually diverges, but they're pretty close together. So let's build a tangent. X minus 64 plus 4. And now we need the slope. And the slope of the cubic, x cube root of x is 1/3 x to the minus 2/3. I can drop 64 in there now. Cube root of 64 is 4. 4 to the negative 2 is 1/16 times 1/3, 1 over 48. And now I can drop 64.1 and use it on the tangent line. 64.1, or 64 and 1/10, minus 64 is 1/10. So what is a good approximation without a calculator? for the cube root of 64.1, 4 and 1 over 480. Hey, got a little practice with that one. Now we're going to do some bounded area in terms of x. And what's this mantra for bounded area in terms of x? Let's get a picture, the square root of x over to x equals 4. So I'm going from 0 to 4, and that's the square root of x. And what's our mantra? To get all these altitudes, top minus bottom. Well, my top altitudes come from the square root of x. My bottom altitude's constant. That's a 0. So if we integrate from 0 to 4 dx, we've got our answer. X to the 1/2 becomes x to the 3/2. Dividing by 3/2, 2/3. From 0 to 4, square root of 4 is 2, 2 cubed 8, 16/3, and if you drop a 0 in, you get 0, so 16/3. Now, what happens if we want to get the same area, but instead of vertical rectangles, what if we make a whole bunch of horizontal ones? Well, I need to know these distances. And it's going to be right there. There's a dy, a little change in y right there at the end. So I got to write things in terms of y. And if the square root of x equals y, then those x distances all the way over there, all the way to here, all the way to here, those are the x distances that I'm generating from what function? Y squared. All right, so y squared, well, I shouldn't call it a function, but the inverse. All right, so y squared. Each of these distances is a y squared distance. And each of these distances is 4. And I'm going to cut those distances away, all right, from the big rectangle, which is 4 times 2. 8 units is the big rectangle. All right, let's see. So, right minus left. There's the right distance, the left. From what to what? 0 to 2, with widths measured on the y-axis. All right, so that becomes 4y minus y to the 3 over 3, and we're going from 0 to 2. Let's hope we get 16/3. 4 times 2, 8 minus 8/3. Do a little bingo, bango, bongo. 24 minus 8 over 3, 16/3. It is indeed the same. Now let's rotate around the line y equals 10. So here's y equals 10. Here's our picture again. This is going to be in terms of x from 0 to 4. So we have to have a big R. That's our big R. Our big R looks to be constant. Our big R looks to be constant. Yeah, so we're going to get a big Hawaiian punch can full of nice Hawaiian punch when we rotate that around 10. But we've got to take away, so that's my big R on this side, this is my little r on that side, and how do I figure out what that distance is? Well, if this is 10, I think I'm taking away that, and what assigns those altitudes? Square root of x. All right, so we've got pi, 0 to 4, big R, 10 squared minus little r is coming to us in 2 pieces, 10 minus the square root of x, we got to square that, dx. And there, just the calculation, we're not actually going to do it out. Now let's rotate around y. Instead of y equals 10, how about we do x equals 10? Okay, and each day we'll pick a different value to rotate around, so there we go. Now we got to get our y squared picture from 0 to 2. So we got pi, 0 to 2, and x equals 10. I hope I said x equals 10. So we got a big R here. What's our big R? Our big R is connecting to the outer edge, which is actually y squared. So, or these x distances, right, are y squared. That x distance comes from squaring the y value. So if I square 2, from here to here is 4 units, and we know that from the previous problems. And I have a smaller r, which is here actually. That's my small r. And I wrote it as a capital, excuse me. That's my small r. This is my big R. That's my big R. That's what's getting rotated around. Okay, so let's look at big R from here to here. Well, that's 10 minus this x distance. And what is that x distance? It's y squared. So there's my big R. I have to square it. What's my little r? Little r appears to be constant. It's that distance to this distance. And I hope you say that's 6. So we got to get that a little bit of dy. And I think we're stacking up big R's, taking away a little r rotations. And I hope that I have not made a mistake. Okay, so that takes care of that. Making some space here. I don't like that eraser. Do I have a better one somewhere? Will I spot it? Yes. I'll be right back. All right, that's it. Erase faster with this, so in the long run, we want to use the cloth. Now, we should be doing some quick problems here. F of x, big F of x, 2x times square root of 2x plus 3, and we want to find the derivative at 3. So we got to do the product rule. We're right here. Product rule and chain rule. So f of x is equal to the derivative of the first times the second plus the derivative of the second times the first, 2x. All right, so we'll cancel these 2's. We'll drop in a 3. So that's square root of 9 is 3, times 2 is 6. So we're doing f prime of 3 right now. We're just dropping it in. And here we get 3, 6 divided by 3 is 2. So I'm getting 12. But I'm really close to the board, and that always bothers me. Okay. All right, now, I hope you can see this and go, oh, that's the derivative of x to the 5th. I see that. And so I'm going to change this because I think it's, okay, so that answer was derivative of x to the 5th is 5x to the 4th, drop in a 2, and you got 8. All right, so I think we've actually done that problem before. I want to do x to the 4th minus 16. I think it'll be easier to show over here. All right, now, I like that one because it reminds me that I had a little bit of trouble 15 lesson sets ago. So I'm doing that whole process that I think is necessary at the Algebra 1 level. We wouldn't start with this problem. We'd start with something like x minus 2 times what equals x squared plus 5x minus 3. Okay, so x times x is x squared, but now I'm at minus 2x. I want it to be at 5. So let's make this an 8 so you don't see any same numbers. So right now I'm at minus 2x. I want 5x, so I need another 7. And now I'm at minus 14, and if I want to get to minus 8, I got to add 6 over x minus 2. All right, so I do a lot of that because I don't think students understand what long division gets them. And this, I think, is a good precursor to synthetic division and long division. I no longer teach either. We do these in our head. So if this is going to be, and we're going to show why it's the derivative of x to the 4th in a minute, but we're doing it algebraically right now. And the derivative of x to the 4th is 4x cubed. And if I put a 2 in here, I should get an 8, an 8, an 8, and an 8. All right, so x times what is x to the 4th? X cubed. Now I have minus 2x cubed. I don't want it, so I got to multiply by 2x squared. But now I get minus 4x squared. I don't want it, so I got to multiply by 4x because that's getting me minus 4x squared. And now I've got minus 8x. I don't want minus 8x. I just want to put an 8 there. And 8 times minus 2 gets me minus 16. So we practice that. And I haven't done it in, quite a while. So I was a little awkward on the explanation. But numbers speak for themselves after you practice them long enough. So let's drop a 2 in. 2 cubed, there's 1/8. 2x squared, there's another 8. 4 times 2 is an 8. And there's our last 8. There's our 4 eighths if I drop a 2 in. Okay, so our answer is 32. Now, how did you see that without any work is to recognize what a derivative is. It's the limit that we're looking at, and that can be expressed as x to the fourth, and I put a 2 in, I get a 16, and if I put a 5 in, a 4 in, a 3, a 2.5, a 2.001, some x value that's heading to 2, I'm going to get something like that. And I don't know what x to the fourth is, 2 to the... I suppose I could do it, right, with calc. That's how I did the squaring and cubing, but I won't do it on your time. So what do I have here? I've got y2 and I got y1. y2 minus y1, and I've got x2 and x1 in a kind of a generic way. And that's what's going to allow me to say that I'm looking at f prime, if f of x is x to the fourth, then I'm looking at f prime at 2, which is 32, 4/8. Now the other way to think about it is that from 5 to 2 is a horizontal distance. From 4 to 2 is a horizontal. From 3 to 2, what are my horizontal distances doing? They're getting smaller and smaller and smaller. 0.001, 2.001 to 2 has a horizontal distance, but it's getting smaller and smaller. And if that horizontal distance is getting smaller and smaller, then this is the same thing as seeing 2 plus h, here's your 2.001 to the fourth, minus 2 to the fourth. And h goes to 0. Okay? Because what's another way of writing this x value? 2 plus h. Right? How would I get from 2 to 5? My horizontal distance would be 3. From 2 to 4, 2. Okay? So that's a rehash of a discussion we've had many times, but I think it's got to be talked about because what are the most important 2 things we study in calculus? Differentiation and integration. That's more important than memorizing the product rule, is understanding what differentiation is. All right, so that takes care of this one. Now I can start working right on top of this. So we want, I'm giving you the derivative of the function is minus sine x. We're going to find the function, and we're going to figure out how to make pi turn into the number 4. Well, whose derivative is the minus sign? That's the cosine. So if I integrate, I get cosine x plus c. We drop pi in. Pi is 180 degrees to the left there. 180 degrees, and that cosine value is -1. And so if I put pi in, that's -1. If I want to get 4 out, I add 3. There's your practice for that. Bounded area between 2 graphs, x squared minus 4x, which I think if we put in factored form, gets us 0 and 4 for points for roots, 0, 0, and 4, 0. And we just want the calculation. Y equals 5 is up here. So it probably intersects at 5, 5, 5, and -1, 5. And I think if we set this to 0, we can see the factoring that comes out of this. X minus 5, x plus 1 equals 0. So we now have our borders for integration from here to here. I'm going to do an infinite number of what? Top minus bottoms. From -1 to 5. Top 5. Bottom is written in 2 parts. What was it? X squared minus 4x. Put that in brackets. I'll give it a little bit of thickness. Each one of these has a dx for a width. Width times heights. Infinite number from -1 to 5 gets us our answer. And we're just doing that, not actually doing the math out. All right. That takes care of that one. average value for a function. Just seeing if you understand what average value for a function is. You take the function and you integrate from a to b, and you divide by b minus a. And I will do, maybe on the next video or the one after it, the average value of the temperatures in New England from summer to fall. I'll do something like that. I think I may have already, but I don't have a great memory. So b minus a, 2 minus 0, from 0 to 2. What was our function? 9 minus 2x. And you can see a situation materialized in one of the next lesson sets with some trig. We'll find some average temperatures over a period of time. All right. Keep my discussion to a minimum here. I'll try to. I'm not doing a great job of that. F and g are inverses. And f of x is x cubed minus 4x. And we want to find the derivative of its inverse at 15. So f of x equals x cubed minus 4x. And the kicker here is numbers in, numbers out. This is going to kick out a 15. So, see if you can pick on your fingers what works. Sure looks like 3. So f of 3 equals 15, and the derivative of this is 3x squared minus 4. If I put a 3 in there, it looks like I get f prime of 3 equals 23. Well, then I now know that g of 15 equals 3, and g prime of 15 is equal to 1 over 23. And we've discussed why in earlier lesson sets. So it's just practice now. Just practice. Good old Allen Iverson. All right, just practice. A little something before your time. Well, maybe not. Who the heck knows what the age is? It's not a classroom anymore. It's not high school. I think there's quite a few seniors that look at these. All right, so dy dx equals 2x, y minus 5, y of 0 gets us 12. So we know what that answer is going to be. It's going to be 7e to the x squared plus 5. All right, so let's find out why that's going to be our answer. It's always good to put an answer next to the original. It's always good to do this, because then if you understand what you're doing, you don't have to do it. Sure looks like that became a positive. And how do I get to 12 from here? I think I need 7. And it looks like that's integration. All right, so let's do dy over y minus 5 equals 2x dx. Let's integrate. ln of the absolute value of y minus 5 is equal to x squared plus c. Let's do e to the y minus 5 equals, I should put plus minus here, but I don't feel like it. So e to the x squared plus c, which is the same thing as e to the x squared times e to the c, and we call e to the c. What do we call e to the c? We call it a. And minus 5 on this side, all right, becomes what on the other side? So this is y over here equals minus 5 on this side becomes positive 5 on this side. If I put a 0 in, e to the 0 is 1. 1 plus 5 equals 12, 7. Right, so doesn't hurt to know that you don't have to work if you don't want to, which is why mathematicians simplify things. They don't want to work. I don't think that's true at all, but on some level, there's some truth to that. All right, dy dx equals 2x cubed, which has a root at 0, sign change, x plus 4. I haven't even asked a question yet, so I'll have to ask a question. Negative 4, no sign change. And 5, we get a sign change, linear sign change. If I put a big number in, I'm going to get a big number out. So here's the graph. That's a cubic root here, so it's got a little squiggly quadratic over here. So that's what our graph looks like. So I think we're looking at first derivative here, yes? So what would be a good thing to ask about How many points of inflection does y have? And you're looking at the first derivative. I'm going to ask several questions. Well, I see 1, 2, 3. I see 3 points of inflection because I go from decreasing to increasing, which means my second derivative, if I'm going from decreasing, my second derivative is negative, then it equals 0, and then it's positive. That's where you get points of inflection, when the second derivative changes from positive to negative and equals 0, or vice versa. What else can I ask? When is y increasing? Y is increasing when its derivative is positive, and that goes from negative infinity, technically, to negative 4, union negative 4 to 0, union 5 to infinity. So the ability to answer this question is either a sign chart but a sign chart wouldn't have told you how many points of inflection you had. This does. I think I told you that in the Algebra 1 videos. It's more useful to be able to graph these things. Okay, so that takes care of that one. Oh, I did ask. Oh, local max. Where will we get local maxes and mins if that's the first derivative? Well, it's 0 there, but it never changes sign, so we're not going to get any local, going up, any local mins there. But here we go from positive to negative slopes, from positive, and it's decreasing, so it's concave down. All right, so we have concave because it's decreasing, and it equals 0 there at what? At 0. So we're going to get a local max here, and I guess that's what I asked for over here. And over here we're going to get a local min because we've got negative slope values and then positive, and it's concave up there because I'm increasing. So over here at 5, y would have a local min, and over here at 0, y would have a local max. Hopefully you can replay that if you want to hear it again. I do talk fast. The way I talk fast is because I know we're after volume here. And over time, I'm going to ask the same questions, same questions, same questions, same questions. Yeah, you can hear it when I talk quickly down the road. And I kind of know that. But I got to get us on the road. So what happens when I go to 0 for these? Then we get rid of the big players. Get rid of the big players. And what am I looking at? I'm looking at 5 over 4x. As I go to 0, I'm going to get a sign change. 5 over 4x. If I put negative 0.001 in, or positive 0.001 in, right? This is going to fit negative to infinity times, and this is going to be positive. So this limit does not exist. DNE. I'm getting sign change. All right. Cosine of x over 5. At this stage, I hope you know that it's 5 times the sine of x over 5 plus c. Hope you don't even have to do it. Don't have to do u substitution, but go ahead. So u substitution will let our u equal x over 5. We'll let our du become, so this is multiplication by 1/5. So it's 5 du over here equals x dx over here. Just dx, excuse me. So the intermediate step is, yes, multiplied by 5. We have 5u equals x, and now we have 5 du equals dx. So our dx is now 5 du, and that's our u. Hope you can see why I have a 5 out here. Hopefully the numbers are speaking for themselves at this point. All right, can you do the next question without having to write it out? All right, so the next question is x cubed plus x squared y minus y cubed equals 5. So y prime should become 3x squared becomes minus 3x squared on this side. 2xy becomes minus 2xy on this side. x squared dy, so we're dividing by x squared, and then we're looking at minus 3y squared division. Okay, so that should be y prime. So we have 3x squared dx plus 2x dxy plus x squared y, x squared dy minus 3y squared dy equals 0. We don't want to have to do that too often, right? So everything with dx, when I divide everything by dx, that one cancels, that one cancels. I'll put the y next to it. So I hope you can see why I moved those to the other side. And then I have dy times x squared minus 3y squared. So that's division, multiplication on this side becomes division on that side, and that's the thought process, the implicit differentiation. All right. All right, so I got a cubic y equals, and I'm going to try to do this in my head, and then we'll do it with the calculus. Y equals x cubed plus 9x squared plus 31x plus, do I want 31? No, let's keep it smaller. Let's make that 5x. This probably doesn't have any local maxes and mins, and I'll show you why later. And let's just add 2 here. So I'm changing that a little bit. So I want the equation of line tangent to the point of inflection. Okay, so let's just look at this. Completing the cube. If you look at x squared and multiply that times x plus 9, you've got a cubic that looks like that. A double root at 0 and a single root at -9. So I didn't look at that before I started drawing. So let's make this minus 9x squared, changing things up. Okay, so now we get the drawing that I wanted, like that. Now where's the point of inflection? Turns out it's right there. And it also turns out that it's 1/3 of that distance from here. It's at 3. And if you want to see why that's true, geometrically, you got to go look at the completing the cube videos. All right, so the quick way of getting the point of inflection is simply minus b over 3a, the average of the roots. And the roots were 0, 0, and 9. If you add that up, divide by 3, you get 3. And what's 9, and this is 1, right? 3 times 1 is 3 into minus b. 9 divided by 3 gets us 3. So minus b over 3a gets us 3. And if we plug a 3 in, you only have to plug it in here. You get 27. So if you add it to what goes there, you're going to find out that that morphs into a minus 54. So you can do this in your head. Minus 54 plus 15 minus 39 plus 2 minus 37. So it looks like my point of inflection is 3 comma minus 37. And then we almost have everything we need in front of us to look at the rate of change there. The rate of change there is c minus 3a h squared. We have all that. We've got c. You could do it in your head. 5 minus 3. A was 1. H was 3. So there are maxes and mins here. Okay, we didn't know that because these are both positive. That's a big enough negative to create maximums and minimums. All right, so what do we got here? Minus 5 minus 27 minus 22 x minus 3 plus 30 minus 37. All right, now, if you want to put this in graphing form, then all you have to do is take a, which is 1, x minus 3 cubed, and that's the graphing form. So we know that 5x plus 2 is the tangent at the point of intersection, so we're going up quickly. I don't know what those y values of max and mins are yet, but I do know that this is going to be going down at 3, negative 37, so I'm going down here, and I'm really running out of room, so I got to miniaturize this graph. So we'll call this 5x plus 2 minus 337. Back up again. That's what your graph's going to look like. And if you want that x value, it's going to be measured from 3, and we're going to go back the square root of 22 over 3. And then you got the x max and min values. That one's going to be positive instead of 3 minus, 3 plus. I think that's useful to know. But let's do it with calculus. Let's see all those numbers appear. And keep in mind, on this particular situation, you're going down fastest there. That's a minimum slope value, negative 22. And what is the derivative of this? The derivative of this is a quadratic. It's a quadratic. What does a quadratic have? A minimum. And that y value is that minimum slope. So we'll put this quadratic into graphing form in a moment. So 3x squared minus 18x plus 5 plus 5. That's our derivative. That's one of these. Now where do I get our minimum? That's what we studied in our Algebra 1 to trig. Minus b over 2a. Minus 18 becomes positive 18. 2 times 3 is 6. Oh, yes, 3. 3 was a very important x value. And what happens at 3? We have a minimum slope. But what about y double prime? 6x minus 18. What happens at 3? Oh, that equals 0. We have a candidate for a point of inflection. And what are the numbers that I plug in that are smaller than 3 going to get me? Negative values. If I put bigger numbers than 3, positive. Oh, I'm changing from negative to positive. Concave down to concave up at 3. And what is my slope at 3? I plug it in to the slope function. 27 minus 54 is minus 27 plus 5. Notice the 2-to-1 ratio when I plugged in a 3. That only happens. This I put in a 3, I got 27. This one is minus 54. That's twice the size of that and opposite. That only happens at the vertex of the quadratic, so we have a minimum. And if we plug 3 in, our slope there is going down at 22-to-1. And then if I plug 3 in here, I get, well, I think I said minus 37 or something. I'm not going to do it again, but it's all matching up. One more problem. Actually, two more problems. Because I just remembered that I said I like to introduce something, look at it briefly, and then stop the class and go, hey, does anybody remember how to take the arctan of 3 times x? Well, I think y prime of 3, derivative is a 3 here, right? So we take the derivative of that, that's in the numerator, over 1 plus what's inside squared. Now these get a little tricky, and when we do the derivative of arcsecant of x, they get even trickier because when you integrate these things, right, you might get confused with an ln function. But no, if you did the derivative of the ln function, there'd have to be a variable in the numerator. And there's no shortcut to getting good at integration. You have to practice, practice, practice. Thank you, Alvin. Al Iverson. Yep. Just practice. All right, last problem. F of x equals the sine function. I said 2 pi over 3. I'm going to change that. How about we do 19 pi over 6? Write the derivative of the sine function at 19 pi over 6. Okay, your brain had to go and think about the circle. And I hope you've said, whoa, there's 18 pi over 6. There's 18 pi over 6. I want this to be broken up into 6 parts. 1, 2, Yeah. Anyway, cut to the chase. I'm over here, right, at 19 pi over 6. 30-degree reference angle, minus 1/2, minus root 3 over 2. Hopefully you have the foundation to do that. If not, time to go to the trig playlist, look at unit circle introduction to the unit circle, get some practice there. It only takes a day or two, 5 minutes. And you can do that. Most of my students at the Algebra 1 level can do this after 4 days. Not in their heads. Well, some of them can. But, you know, most have to draw it for a while, but can draw it and do it. All right, so what's the derivative of the sine function? Cosine function. The cosine is minus root 3 over 2. X minus, I think I said 19 pi over 6. And at 19 pi over 6, the altitude's minus 1/2. And so last thing we'll do is graph the sine function. That's 1 period, right? 3 pi, so 2 pi is to here, so 3 pi is to here. We're right about here. That's where 19 pi over 6 is, and we're going down at approximately negative 0.87. I've asked you to memorize those numbers. I have to tell you, having taught for nearly 50 years, I start telling people to memorize those. I hand out a sheet 3 months into a term, and I ask the class, and only 2 or 3 kids have memorized it. You got to put some effort in. Memorize it. Make a little journal for yourself. Right? It pays dividends in the long run. The last lesson set, I asked you to, maybe you can tell me e to the what? E to the what gets you, how about what's an easy number here? 18. Now this only works locally. Eventually these approximations with exponential functions diverge. But locally we can get a good approximation here because I know what 18 is. 18 is 3 squared times 2. And I know what 3 is. 3 is e to the 1.1 squared times e to the 0.7. Right? So 2 times 1.1, 2.2 plus 0.7, 2.9. You go and put e to the 2.9 into a calculator, you're within a couple of hundredths of a decimal place of 18. That's good, because then we can eventually build the rules of logarithms. Right? And not that you do, yeah, I'm rambling, but not that we do this anymore. I don't think we do much with the change of base formula, because calculators now can do that. Right? Calculators now have a place to put the base and to put the argument. But you know, it doesn't hurt to say, well, a lot of good learning. What's the exponent you put on top of 2 to get a 3? Well, you got to change it to e notation. So you're going to do log e to the 0.7 gets us e to the 1.1. So e to the 0.7 to the what? I'll make a question mark. Gets us e to the 1.1. I'm really messing here. So let me rewrite that this way. E to the 0.7 to the what exponent gets us e to the 1.1. There, that's better. That means that 0.7x has to equal 1.1, and therefore x has to equal 1.1 divided by 0.7. Now what is 1.1? It's the ln of 3. What is 0.7? An approximation for the ln of 2. That's where your change of base formula is coming from. Right? And it's useful to know where things come from. Because if you're only doing do this to get that, I'm not sure if you're really making the kind of gains you need to make. All right. I'm losing my breath here. Whew. Okay, happy holidays. Tomorrow's Turkey Day.